Hey guys, Matt here today. Welcome back to another video. So today I'm going to show you guys how you can solve various 2D grid or matrix problems using depth first search. So specifically, I'm going to show you an easy recursive template that you can reuse for many of these types of problems. Okay, so to start off with, let's look at the following coding question. The problem states, given a 2D matrix of zeros and ones, the first square is a 1, and all ones are adjacent. How many ones are there? So the brute force solution would be to simply iterate over every single cell, counting the number of ones. But the key information in this problem is that it tells you all ones are adjacent. What this means is that we can traverse over only the ones using any sort of graph traversal algorithm. And that will allow us to ignore the zeros, which increases the efficiency of our solution drastically. So DFS is a graph traversal algorithm. So why do we want to use it on a grid? Well, intuitively, many grid type problems can be transformed into a theoretical graph representation. For example, you can transform this grid right here into this graph of ones, where you basically take every cell that is a 1 and create a node. And then from here, it should be clear that we can then apply whatever graph traversal algorithm we want in order to very easily solve this problem. Okay, so here is the pseudocode solution to this problem. So this version of DFS uses recursion along with the calling stack instead of an actual stack data structure. This makes our code both clean and really easy to write. Specifically, we can have a stopping condition at the beginning that controls when to stop traversing. This means that down here, we can blindly call DFS on every neighboring cell without having to check the necessary condition 4 times, once for each neighbor. Okay, so I want to just really quickly go over the general structure of how I wrote this method, because pretty much every single DFS method you write in order to solve these types of grid traversal problems is going to follow this format. Step 1, you want to check the necessary conditions in order to keep traversing. So first, you want to check that your cell is actually inside the grid and not outside the grid. And that's going to be the same for every single grid traversal problem. But for this specific problem, our necessary condition is we only want to keep traversing on the ones. So we stop if our current cell is a 0. Then the next component of your DFS method is going to be processing the cell. In other words, you're going to process the data in this cell in order to build up your solution. So this question, we want to find out how many ones there are. So then all we have to do for this step is we increment our counter. This next part of code though, matrix cell equals 0, this just means we set a cell to 0 after we've visited it in order to prevent us from traversing on cells that we've already seen. Then the final component of your DFS method is always going to be calling DFS on the neighboring cells as needed. For this specific problem, it talks about adjacent cells. That means we can call DFS in 4 directions. So that's what we do here. And these are the 3 major components that you're going to see yourself rewriting for these types of problems. Okay, so let me just run through this algorithm on our example right here. So first, we call DFS in the main method. And the overall idea of DFS is it's going to traverse over this entire chunk of ones and count it for us. So we call DFS on the first cell. And the cell is a 1, so we should keep going. So then we set the cell equal to 0. We increment our count, which I'm going to do down here. And then we call DFS on the right, left, top, and bottom. So we actually did call DFS right first. But for these 3 other calls, they're all going to return immediately since these 2 are out of bounds and this one is not a 1. And then, so anyways, but we're going to go on to DFS right. We're going to do the same thing here. And then it's going to call DFS right, which immediately returns. Then DFS left, which immediately returns. DFS top, which immediately returns. And then it's going to call DFS bottom. We're going to do the same thing with the bottom cell. Right, left, top, bottom. So DFS usually uses a stack. And what we're really doing here is we're pushing all these DFS calls, or you can imagine them as neighboring nodes, onto the recursive stack, or the actual stack. We're not using a data structure stack, we're using the calling stack instead. Anyways, so then here we call DFS right. And then the reason it's called DFS is because we fully explored this branch first. And then this DFS right call calls DFS right again. And then this calls right, immediately returns left, immediately returns top. And then bottom immediately returns. Then we go back to our calling stack and we still have this DFS call, which we haven't processed. So that's going to be the final step. And now we have our answer 8. So what you'll notice is that, well, actually this is a very dense grid, but in sparse grids, it's even more important to use DFS rather than traversing over the entire grid. But really, we only process cells that are ones. We didn't have to look at every single cell. So yeah. Okay, so before we jump into this LeetCode medium problem, I just want to talk about some general problem solving tips. So generally, if a problem states something about cells being adjacent or about movement in 4 directions, oftentimes the solution allows for the use of a graph traversal algorithm, such as depth first search. Specifically, if the problem involves exploring the grid, oftentimes that's a giveaway. On the other hand, if the problem involves optimization, such as maximizing a path sum, or if you already know everything about the grid, then the answer is probably not graph traversal. So hopefully that's a good baseline, but you'll definitely be able to build this intuition over time. Okay, so let's jump into this LeetCode problem. So the problem states, given a 2D grid map of 1's land and 0's water, count the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all 4 edges of the grid are surrounded by water. So this is very similar to our previous problem, except in the previous problem, we had one chunk of ones and we were trying to count how many ones were in that single chunk. Except in this problem, we're trying to count how many different chunks of ones, or how many different islands there are in our grid. So, for example, in this first one, we really only have one island because every single one is adjacent. There aren't different groups of ones in our grid. But in example 2, we have this upper left island, this middle island, and this bottom right island. So how do we approach this problem? Well, first of all, it's talking about counting and it's talking about adjacent lands or cells. So that's sort of a giveaway to use graph traversal or DFS. And also we really don't know much about the grid. It seems like we need to explore it. Anyways, if we think back about what our DFS method really does, is it traverses over an entire group of ones that are all adjacent. For example, if we call DFS one time on this upper left blob, it'll traverse over this entire upper left blob. But it won't traverse over the other islands, just the upper left. So the idea here is that every single time we call DFS, we fully explore one island. And since our answer is the number of islands in our grid, all we have to do is count how many times we have to call DFS in our main method. And the reason for that is every DFS call zeroes out an entire island. So how many times do we have to call DFS before the entire grid is zeroed out? Okay, so now it's time to code up our solution to this problem. So basically what we're going to do is we're going to turn our pseudocode from earlier into Java code. And this is relatively straightforward. There's just a few different things we need to do. But anyways, if you recall, the objective of this method is to traverse over an entire island. That way, all we have to do is count how many times we call this method, and we have our answer to how many islands are in our grid. So if you'll notice, we have these 2 extra parameters here. And these parameters are basically going to be where we are in our grid. And we also need to pass in our grid. So unlike before where we used like a pseudo cell object, this time our cell is going to be represented by coordinates. And let me just switch this around. Actually, it'll be more clear if I use like row and column. So let's just code up our 3 components. First, we need to check that our coordinate is not out of bounds. And we need to make sure that it's actually a land or 1 so that we can keep going. So if grid row call, or actually, sorry, first we need to check out of bounds. So if our row is less than 0 or our column is less than 0, we are obviously out of bounds. And then if you remember, row is like this. So if, well, or if row is greater than grid dot length minus 1, or column is greater than grid of 0 dot length minus 1, then we return. That's our stopping condition. Also, we have another stopping condition. If grid row, if the cell is a 0, we need to stop. We don't want to keep traversing. So that's the first component. Now the second component is process cell. What's the goal of this problem? We want to count how many islands. So before we incremented every single time we encountered a 1, we don't need that this time. All we have to do this time is 0 out the cell. And now step 3, call DFS as needed. So all we have to do is call DFS on the left, top, bottom, and right. And again, because of this stopping condition, we don't have to check these. We just write it up here and we're good. So yeah, so we need to do a tiny bit of math. So we need to call on the left. What we're going to do is we're going to keep the same row, except column minus 1. And then we're going to call on the right. And then we're going to call on the top. And then we're going to call on the bottom. So yeah, this should be very easy to code up. It's the same thing for every single problem. And let me fix this typo. So now we have our DFS method. This method will traverse over an entire group of 1s and 0 them out. So how do we use this in our main method? Well, all we have to do is iterate over the grid, like so. Your typical nested for loop. And then we call DFS mark when we encounter a 1, meaning we've encountered some sort of island. So if 1, oh, actually it's an array of chars. Okay, so all I did was change these checks to the character 0 rather than the number 0. I didn't notice that the parameter was a char array. But anyways, so yeah, we check if it's a 1. And then if so, we call DFS mark. And we pass in our row and column. So this method is just going to traverse over that entire island and 0 it out. So let's keep a counter right here. And then every single time we call this method, we increment our counter, meaning we've gone through another island. And then all that's left to do is we return this answer. And hopefully this works. And hopefully it worked. Okay, so yeah, it's actually extremely runtime efficient, faster than 100%, and that's what we like to see. So yeah, we finished number of islands, and again, you write the DFS method following these 3 steps, and then you use that DFS method as needed in your main method. And now we're going to move on to a slightly harder problem. Okay, so this problem is called Pacific Atlantic Water Flow. It's a bit complicated, so please pause the video and take a second to read it, think about it, maybe even try it for yourself on LeetCode.com. Okay, and now that you've done all that, let's get started. So the Pacific Ocean is the top and left sides of the grid, and the Atlantic Ocean is the bottom and right side. Basically, the problem is asking you from which cells can you traverse to both the Pacific Ocean and the Atlantic Ocean. And the condition of movement is defined as 4 directions, except you can only move from higher cells to lower cells. So if you remember our DFS template here, check the necessary conditions. Before, we only had to check if the grid was out of bounds and if it was a 1. Now, instead of checking if the cell is a 1, we're going to check if the cell is lower than where we came from. And that's going to be step 1. Then step 2, process cell, what we're going to do is we're going to add it to a list of cells that can reach 1 ocean. And then step 3, call DFS as needed. We're going to blindly call DFS on the top, right, bottom, and left, just like before, because step 1 is our stopping case, and we don't have to check for it again. So let's get started. So I encourage you to try this problem on your own to fully understand what it's asking. But anyways, let's get started. So again, we're going to write our DFS method. What is the goal of our DFS method? Well, we want to fully traverse from one ocean and see which cells can reach that ocean. So really we're doing it sort of in reverse. Because if we just traverse from one cell and see where it touches, it'll quickly expand the grid, and that's not time efficient. But if we traverse starting from each ocean and see which cells the ocean can reach, then we're not going to traverse over nearly as many cells. But anyways, so we can only flow water from a higher valued cell to a lower valued cell. So if we're flowing from the oceans to see where it can reach, we want to check that the new cell is higher valued than the old cell. So let's get started. Okay, so I've gone ahead and written out the method signature for our DFS method. So it's a little bit more complicated than number of islands, but it's pretty straightforward if you think about it. So of course we need the matrix, then we also need the row and the column, and now we have these two extra parameters. So if we think about what we need to write these three components, for check necessary conditions, we need to check that the current cell is higher value than the old one. How do we get the old value? Well, that's what this parameter is for. And then we also need this parameter, ocean. So if you recall, the way we're going to solve this problem is we're going to see which cells can be reached from the Pacific Ocean, which cells can be reached from the Atlantic Ocean, and then find the common elements and return that. So what we're doing here is we need a 2D matrix to record the cells that we've reached from the Pacific Ocean, and then another 2D matrix to record the cells that we've reached from the Atlantic Ocean, and we're going to pass those in as parameters. So let's do that right here. So Pacific equals new int and then let's copy that for Atlantic. Okay. So now let's just first write our DFS method, and then we can think about how to use it in our main method. So first we check the necessary conditions. Again, we check that our coordinate is actually in bounds. I don't know why I just laughed. Then we return. And now what's our other condition? Well, we can only flow from higher values to lower values. So when we're flowing in the reverse, we can only flow from lower values to higher values. So if our new value is lower, then we need to stop traversing. If matrix row column. Okay, now that looks pretty good for step one. But remember, we also need to make sure that we don't traverse over the same cell multiple times. That's where these two 2D matrices come in. So the idea is during the process cell step, once we reach a cell, we're going to mark it as reachable in the respective ocean matrix. And to do this, we can just mark it as, say, 1. So then if the cell has a value of 1, then we've already reached it, and we should also return. Alright, now we've finished step 1. And these can all be else ifs. That'll probably save us some space. Like not literal space as it runs, but space in our code. So 2, process cell step. What do we need to do? Well, we need to record that our current cell is reachable from the ocean. We also need to set it equal to 1 so that we mark it as that. So really this is just one simple step. Ocean row call equals 1. Okay, and now our final component of our DFS method is call DFS as needed. Again, because we have these checks, I just love pointing out why writing it recursively is so good. Because we wrote these checks at the beginning, we can just blindly call on the left, top, and bottom. So I really should have just copy pasted this, but yeah, we're going to call it on the left, or this the top. And then we need to pass in the ocean, and we also need to give it our previous value, which is the same as our current value. And there we go. Now let me copy paste this 3 more times. And we'll fix this to represent all the neighboring cells. And there we go. And now our DFS method should be complete. Okay, now the final step is how do we use this method in our main method? Well, so we know starting from a cell, this DFS method will traverse to all the cells reachable from that cell. So if we want to find all the cells reachable from the Pacific and Atlantic Ocean, we basically just need to call this DFS method on the Pacific and Atlantic Ocean. So that's really all we have to do. And then this will construct a list of all the cells reachable in our two 2D matrices. And then we can cross-check the two lists and we can form our answer. So right here, we're going to, so the Pacific Ocean is the top and the, actually, okay, so I'm just going to do the top and bottom, then the left and right. So for, yeah, I'm going to do the top first. So for int call equals 0, call less than matrix 0 dot length, call plus plus. We're going to call it on the first row and the last row. So we know that these cells are reachable from the Pacific. These cells are reachable from the Pacific. These cells are reachable, or like the highlighting is bad, but you get what I mean. These cells are touching the Pacific Ocean. So all we have to do is call our DFS method on these cells and pass in the Pacific Ocean, and then call it on these cells and pass in the Atlantic Ocean. So we're going to call DFS on matrix, and then our row is going to be row 0. This is the Pacific first. And then our actual column. And then our previous value is going to be, we don't want to get stopped by the necessary conditions. So we're just going to pass in the minimum integer. And then we're going to pass in the Pacific Ocean here. And then the same thing, except we're going to pass in the Atlantic Ocean. And instead of this, we're going to need the last row. And now we're going to do the same thing. So let me just comment this. This is top and bottom. And this is left and right. So yeah, so DFS matrix, except the row is going to be what's changing and our column is constant. And then Pacific. And oops. And let's copy this. And this is going to be the last column. So that's going to be matrix 0 dot length minus 1. And it's going to be the Atlantic Ocean. Okay, so let's just review our code here. So our DFS method will record all cells. It'll expand from a certain cell and record down all cells that are reachable from a specific cell. And then here, basically we're just calling our DFS method on the border, on the oceans. And then in our two matrices, we'll record the results of our DFS method. So after running all this code, now in our Pacific matrix, we have all cells reachable from the Pacific Ocean. In our Atlantic matrix, we have all cells reachable from the Atlantic Ocean. So now all we have to do is compare the two matrices. Okay, so we're going to return a list of lists. So you can do it like this. I don't know, response. That's what competitive programmers use. And then we're going to traverse the matrix, traverse and find common elements. Really, I mean iterate. I really mean iterate, because traverse implies that we don't know where we're going, but iteration is always the same. Oops. So typical nested for loop. And then, yeah, we're just going to compare. So if Pacific ij equals 1 and Atlantic ij equals 1. Because remember, in our process step, we changed the cell to a 1 if that cell was reachable. So if they're both equal to 1, it means that they're both reachable from both oceans. So if it equals 1, we need to construct a solution. For lists of very small size, linked list actually beats out array list by a tiny bit. And now we're just going to add the coordinates one by one. Sorry, I blinked out for a sec. And then we're going to add it to our response list. So this code found all the common elements and added it to our list. And now all we have to do is return the response. And hopefully this will work. Okay, so I actually hate LeetCode for this, but I forgot this one check that makes sure our matrix isn't empty. But all of the other code was correct. And if we submit, you'll see that we actually have a pretty time-efficient solution. Not that you should trust LeetCode numbers, but if you just think about it, the complexity is very good. And yeah, that's pretty much it. So again, the key part of this lesson is your DFS method. For many of these exploration type grid problems, you can just use the same recipe over and over, where first you check the necessary conditions, then you process the cell, you build towards your goal, and then you call DFS on the neighboring cells as needed. And actually, there's at least 10 problems that follow this exact pattern. So hopefully this was a good video, and I would really appreciate a like and subscribe or any feedback in the comments. Thank you.